Okay. Assalamualaikum warahmatullahi wabarakatuh. And a very good day to all of you. Okay. First of all, I would like to apologize that I couldn't do this week class online live with you. As I have a bit of family matters, so I do this pre-recorded video, and I hope that you watch this lecture. Um, and if you have any problem, if you have any questions, you can always WhatsApp or email to me offline. Okay, I'll try to answer. Okay. Okay, so today, so this week, the second week, we are going to start, inshallah, the first chapter. Okay, the first chapter of aircraft propulsion. So last week was I introduced to you. We did some recap for some of you from engineering background. Most of you already know about thermodynamic fundamentals. But maybe to others, it's a bit new thing to explore. But inshallah, you will catch up. Uh, all of you will catch up. Okay. So why I did explain last week why we need to recap, recall, and or to learn thermodynamic before we learn propulsion or aerospace aircraft propulsion, is that the fundamental part of propulsion engine propulsion, how means how are we going to design engine, etc. It depends on our fundamental knowledge of thermodynamics. It's like if you want to design to take into consideration the aerodynamic of the aircraft, you need to first understand the fundamental of fluid mechanics. So the same as this one, in order to design a good performance of aircraft engine, which is aircraft propulsion, so you need to have the knowledge of thermodynamics. Okay, to need, as a designer, engineer is a designer, so you need to take into consideration those fundamental parts. Okay, so this chapter 1 is basically introduction. So we are still in the introduction phase. Okay, so basically most of the content, maybe some of you already expert, expert than me. You already know better maybe, but we try to share. Okay, we try to share with each other, or maybe try to recap back those knowledge that we already know. Okay, so let's start. Okay, enough talking. So last week, I did mention about these 3 laws of conservation. I think so. Hope so. Okay, so these 3 laws of conservation that we have to obey, to hold. So the first one was about the conservation of mass. So that mass neither can be created nor destroyed. So we have the conservation of mass law. You remember that mass flow rate can be equals to rho AV. Okay, rho AV. Density, area, and velocity, speed. And then second one, total moment. Second one is the conservation of momentum. Okay, conservation of momentum means that total momentum is equal to the force created, which is means that the sum of the force is actually sum of the force. Sum of the force exerted on the system, okay, is equals to MA or MV, M dot V, velocity. Mass flow rate multiply with velocity, or mass multiply with acceleration. So this is actually Newton's second law. Newton second law. Okay, the conservation of momentum. And the third one is the energy neither can be created nor destroyed. So this is the first law of thermodynamics. First law of thermodynamics. Okay, which from this first law of thermodynamics that we we produce the energy balance of the system. Okay, whether it has heat transfer, it produce work, whether it has kinetic energy or potential energy, enthalpy, etc. Okay, next. Okay, introduction to aircraft propulsion. Okay, gas turbine engine has been known to produce satisfactory mechanical power. Okay, so for aircraft propulsion, what are we going to use? We are going to apply the gas turbine engine. So this gas turbine engine can be used in two types of application. First one is aircraft engine. Okay, the gas turbine is used in aircraft engine, and the other one is also used for power plant in industry. Okay, power plant. So because gas turbine engine can produce enough mechanical power to be applied into power plant and aircraft engine. Okay, but it has some drawbacks also due to no reciprocating. It's not a reciprocate engine. Reciprocate engine means like a piston engine. Okay, piston engine is a reciprocate engine. Okay, but gas turbine is not a reciprocate engine. Okay, resulted in few balancing problems, low lubricating oil consumption, and high reliability. Okay, so three main components of a gas turbine is compressor, combustion chamber, and turbine, of course. Okay, this is open system. If you remember last week I mentioned, if for power plant we use closed system. Okay, closed system is normally used in power plant. Right. Open system normally used for aircraft engine, jet engine. Okay. Okay. So this aircraft engine have open system. For open system, we have only three main, the basic. Okay, the basic is only three of them: compressor, combustion chamber, and turbine. For closed system, the basic. We have four components: compressor, combustion chamber, turbine, and condenser to complete the cycle, because it is a closed loop, closed system. So it has to have the last one, okay, condensation. But for open system like aircraft engine, we only need three: compressor, combustion chamber, and turbine. Okay, the basic, of course. And then, okay, so this is the one type of the simple gas turbine system. So we have air intake at the inlet of compressor. Basic, remember again, this is basic. Not the same as those gas turbine that you see in current aircraft engines, but because this is the basic one, in order to produce basic power output, we have air at the intake, and compressor, combustion chamber with a fuel added here. So the combustion process will occur in here, and we have turbine. Okay, that will generate power output or thrust. Okay, yeah, for the engine to propel. Okay, this is the basic, simple gas turbine system. So this is open system. Open system, because it doesn't have condenser. Okay, for closed system, we have condenser after turbine. Okay, to complete the cycle. Okay, next. Okay, in practice, loss occur in both the compressor and turbine, which increase the power absorbed by the compressor and decrease the power output of the turbine. Okay, so if the compressor is lower in efficiency, low performance, so means that there is energy loss. So mean that the compressor need more power. Okay, when the compressor is low in efficiency, means that it need more power to be driven, need power. And when turbine is in low efficiency means that it produce less power. Produce less power. So it less efficient, sorry. Produce less power. Need more power. Okay. Two main factors affecting the performance of gas turbine engines are the component efficiency, of course. So sometimes the compressor turbine sometimes has 60%, 80% efficiency, right? Okay, so and then the turbine working temperature, the maximum we call it TIT, turbine inlet temperature. Okay, because the turbine inlet temperature normally is the maximum temperature that can the turbine blades what we say the maximum temperature that can be used in turbine. Okay, the maximum temperature of the fluid air, okay, inside the gas turbine engine. Okay, the maximum temperature that the turbine can apa tu bertahan, macam tu. Okay, so that's why we need to take into consideration this maximum temperature, because this the amount of maximum temperature will guide us how to design the turbine. Okay, uh, more and more recent technology we try to manufacture turbine with material that can retain, that can accept higher temperature. Okay, so depends on the material used in the turbine. Okay, the overall efficiency of the gas turbine cycle depends also upon the pressure ratio of the compressor. So another factor is the pressure ratio of the compressor. Okay, means that the pressure at the inlet and outlet of the compressor, the compression pressure. The development of some aerodynamic, okay, advanced engines using pressure ratio up to 35 over 1, component efficiency of 80 to 90%, and turbine inlet temperature more than 1650 Kelvin. Okay, so it can goes up until this. Okay, but there are always more and more study. Okay. Okay. Um, wait, wait, I stop. Okay, sorry, we continue. Okay, possible system for combustion. Okay, these are the factors that we have to take into consideration as well. Constant pressure, continuous combustion process, valves are unnecessary. For constant volume, thermal efficiency is higher, greater mechanical difficulties. Okay, I think I'll pass this one first. Okay, this is more important. Okay, so the three components just now that I mentioned, compressor, combustion chamber, and turbine, those are the simple basic components in gas turbine engine. But okay, usually designers we will add other components to the gas turbine engine to make it more efficient, more perform better. Okay, so sometimes we add intercoolers between the compressor, okay, to reduce the power used in the compressor. Okay, so we add intercoolers and reheat combustion chamber, okay, between the turbines. Okay, so before the fluid enter the turbine, it will be reheated. Depends on the how many reheater that we have. Okay, a heat exchanger can also be introduced. We can also include another component, which is heat exchanger. So these refinements may increase the power output and efficiency due to the expense of added capacity, weight, and cost. Okay, of course, by adding those extra components, we will increase in terms of power and performance efficiency, but of course needs more cost. Okay, and add more weight. Okay, so that is weight is the one of the most important criteria that we need to take into consideration when adding extra component in the aircraft engine, gas turbine aircraft engine. Okay. For power plant, maybe it is not really a crucial problem because it is a power plant. But for aircraft engine, we need to take this weight factor into consideration. Okay, two system of cycle. This one just now that I mentioned, open cycle and closed cycle. Okay, you can read this one. This is the simple closed cycle that I mentioned just now. So we must have another component, at least 4 components to complete the cycle. Normally condenser, okay, to complete the cycle because it is a closed system. So this one is a compressor, as usual, compressor. This is turbine and generator. Okay, so for power plant, normally here it is not combustion chamber, but it is a evaporator or boiler. Okay, power plant we don't use combustion chamber here, but we use evaporator or boiler. Okay. Okay, open cycle, back to open cycle. If the gas turbine is required to operate at fixed speed and fixed load condition, okay, the single shaft arrangement is more suitable. Okay, if we have a fixed speed and fixed load, we can use a single shaft arrangement. Single shaft is like this, the basic simple gas turbine. Okay, a heat exchanger might be added. Okay, like mentioned just now, we can also from the basic single shaft cycle, we can add heat exchanger. Okay, before the fluid entering the combustion chamber. Okay, to improve, of course, the thermal efficiency with reduced power output by 10% due to frictional pressure loss. Okay, however, we will lose in terms of power output. So there is always pro and cons. Those additional material, those additional component. Okay, so it depends on what do we want to achieve, what the designers, what the consumer want, whether they want a gas turbine that is more efficient. So if they want a gas turbine that is more efficient, then we may add heat exchanger. Okay, before the combustion chamber. But if they focus more on the power output, want to have a gas turbine that can produce power as high as possible, then maybe this concept, this single shaft open cycle with the exchanger is not very convenient, suitable. Okay, heat exchanger is essential for high efficiency when cycle pressure is low, but become less advantage as the pressure ratio is increased. Okay, because if we have a pressure ratio, okay, normally to explain this, I always try to draw it in terms of TS diagram, but this diagram is not being introduced to you yet. Maybe in chapter 3 with Dr. Izani, but it's okay. I just draw the basic diagram first. So this is a TS diagram of a gas turbine cycle. Normally you will have a diagram like this. Okay, so this is compression. This is S is entropy. Okay, the second law of thermodynamics. T is temperature. This is temperature. So compressor, combustion chamber, turbine, and oh sorry. Okay, it's because it is a open system, so no condenser. Okay, so if the pressure ratio, which is here, is increased, is high enough, then maybe the need of a heat exchanger, because heat exchanger we add here before entering the combustion chamber, heat exchanger, right? But if the pressure, the pressure ratio, which is the pressure at the compressor here, is high enough, it's already been increased, so maybe is less advantage, okay, to add another heat exchanger here, okay, because the pressure is already high, okay, increase, pressure ratio is already increased, so maybe we don't need extra heat exchanger here, okay, because the location is here. Okay, the basic engineering is seldom considered in basic engineering. Okay, next, okay, this one shows a modified form proposed for use when fuel is such that the products of combustion contain constituent with core or okay, so this is another type. Okay, another type of a single shaft open cycle gas turbine with heat exchanger. It's just that this one, okay, this one means that the heat exchanger directed to the turbine first and then combustion. Okay, so it's a bit different than just now. Okay, so this is if the products of combustion contain constituent. Okay, so means that after combustion, after the process in the combustion chamber, we need to like process the products from the exiting the combustion chamber here, okay, in the heat exchanger, okay, before it continue to complete the cycle. Okay, so this is another form. So this cycle is used, maybe we can use this type of single shaft open cycle gas turbine if we want uh, to get rid of this product of combustion. Okay, okay. Okay, so this the previous cycle gas turbine engine just now is much less efficient than normal cycle, since the heat exchanger is transferring the whole energy input instead of merely a small part of it. Okay. Uh, so means that we use more energy input. If you use more energy input, then the efficiency will be lower. Okay. So there's ada separate power turbine. This is separate power turbine, means that we have low power turbine and high power turbine. Okay, means that the fluid inside the gas turbine is being expanded twice. Okay, in low pressure and high pressure. The performance again may be improved by reducing the work of compression. Okay, is improved, reducing work of compression and increasing the work of expansion. Okay, because we expand the fluid twice, so we increase the expansion, so increase power. Okay, so compression process also can be carried out into almost stage by using intercooling. Turbine output can be increased by dividing expansion into two or more stages. Okay, so the same as in expansion turbine, we can also add compressor, low pressure compressor and high pressure compressor. All of this, the objective is to increase performance. Okay, so this one, a more complicated design. Okay, so we have Low pressure compressor, okay, like I mentioned just now. So this is very complicated. Well, not very complicated. May far from basic. So you have low pressure compressor, you have intercooler, you have high pressure compressor, and then we have high pressure turbine, low pressure turbine, and two heater or combustion chamber. Okay, and another heat exchanger here, so it's very complicated. So we can apply this one, no problem. Okay, if we have enough cost, and if weight is not our major factor. Okay, for power plant, maybe we can do this type of arrangement. But for aircraft engine, maybe this arrangement is not very suitable because it use a lot of weight. Okay, we add too much component. But we never know. Okay, depends on how much power it can produce. Maybe it is worth. Okay, so that's why we need to study, to do some research whether this complex plan is worth it or not to be applied to aircraft engine. Okay, if we don't have data, we cannot make conclusion. We need data. We need to study, do case study, and see whether actually is beneficial or not. Okay. Possibility of varying the power output by controlling the fuel supply to the reheat chamber. Okay, this one multiple arrangement. Okay, so another method, to obtain a high performing gas turbine engine without using extra component, heat exchanger, we can also increase the pressure ratio. Okay. Okay. So multi-stage centrifugal compressor. Okay, later on in future chapters, I will introduce about centrifugal compressor, axial flow compressor. Okay, it's lower efficiency than the axial flow compressor. Okay, for large unit engine, axial flow compressor is preferred. Okay, normally in turbofan engine, we will use axial flow instead of centrifugal flow because it has a higher efficiency. Okay, this one you can just read. Maybe I don't go one by one each slide. So some of the slide you can just look at it by yourself. Okay. So okay, twin spool engine. Just now we only see about single spool. Okay, now twin spool. You have low pressure and high pressure. Low pressure compressor, high pressure compressor, high pressure turbine, and low pressure turbine. Okay, so it is called twin spool. Okay, so low pressure part, the low pressure compressor is driven by low pressure turbine, and high pressure compressor is driven by high pressure turbine. So easy as that. Okay, so twin spool is called twin. Okay, for engine with small airflow, the high pressure compressor is of centrifugal type. Okay, small airflow, we can use centrifugal compressor. Okay, this is because at the high pressure involved, the volume flow rate is low and the blading required for an axial compressor will be too small for good efficiency. Okay, so that there is pro and cons. And then closed cycle cycle at high pressure. Okay. Okay, so like I mentioned just now, we will look at the turbo machinery in future chapters. Okay. Oops. Typical closed cycle gas turbine. Simple closed cycle, not very simple. Unfortunately, so figure 1.8, a closed cycle turbine, a closed gas cycle gas turbine. There's pre-cooler, you have auxiliary cycle. So this is a bit complex, but this is mainly used in power plant. Okay. So maybe not too important for you. So it's about close. Okay, so these are some of the example. I think most of you know about this. So we have first greatest impact of gas turbine. Impact of gas turbine, application of gas turbine in aircraft propulsion. So first one we have the Whittle engine in 1937, the jet aero engine. Okay. So with air intake, etc. Oops, sorry. Saya sudah padam. Okay. And then we have Rolls-Royce Olympus turbojet engine. So turbojet engine is the first aircraft engine, jet engine, and then from turbine we develop turbofan and turboprop, right? Okay, being used as a gas generator. Okay, at high subsonic speeds, a propulsive jet of smaller mass flow but higher velocity is required. Okay. Uh, okay. For at subsonic speed, but we in order to use to uh, to provide high velocity, normally um we use turbojet, right? Turbojet is used mostly for to achieve a high velocity, a high speed of aircraft. But now we can also use turbofan, okay, by adding a bypass duct, right? Okay. So this one, I think you already know the function of turbofan. Okay, part of the air delivered by low pressure compressor or fan. Okay, bypass the core of the engine to form an annular propulsive jet. Okay, I think this is the function, the main function of turbofan. The main difference of turbofan than the turbojet. Okay, I think this one you already know. This result in jet with lower mean velocity. Okay. So I skip this one. I think you are more expert than me on this. Okay, low fuel consumption, high bypass ratio. So all turbo machinery are in axial type, annular combustion chamber. Okay, so we will look, as I mentioned just now, we will look into the combustion part and turbo machinery part in future chapters. Okay, industrial application. Okay, okay, the aircraft power plant can make use of kinetic energy of the gas leaving the turbine, whereas it is wasted in the types of in the type gas turbine. Okay, so we see that for aircraft, the kinetic energy is very important because you want to propel the engine, right? Okay, so unlike other gas turbine engine for power plant, etc., the kinetic energy may be wasted. But for aircraft, it's very useful, this kinetic energy part, because this kinetic energy that will be used to propel, to produce power, thrust power, and to propel aircraft. Okay. Okay, natural gas turbine, so these are all types of gas turbine, right? Okay. Gas turbine design procedure kecil sangat a bit small, sorry. So this is so one of the reason that you learn this course is that you know the procedure, what are the steps that you need to take into consideration in order for the preliminary design of a gas turbine engine, right? So this is like a flow chart suggesting what are the factors and the methods in order for us to design a gas turbine. So first, we need to choose a cycle, type of turbo machinery that we want to use. What are the thermodynamic design part? Remember, here, we need the thermodynamic design point studies. Okay, that's why thermodynamic is very important. Okay, so those are the criteria. Okay, of course, customer requirement, market research also need to be added. Mechanical design, displays, component risk. Okay. I have more important things. Okay. History of the development of gas turbine for power generation. Okay, so from 1968 to 1993, we have the gas turbine engine have been developed. So we have increased, the power have been increased from 42 megawatt to 160 megawatt. Thermal efficiency also, pressure ratio, turbine inlet temperature, okay, airflow. Okay, So this is the evolution of the development of gas turbine. Okay. These are the important part. The last 10 slides are the most important part, because I'm going to introduce to you some of the performance parameters that you are going to use several times. Okay. The performance parameters. Okay. This is the most important parameter, which is trust force, trust power, trust. Okay. This is the main performance parameter for aircraft propulsion. Okay. In order to evaluate the performance of an aircraft, the properties, the parameter that we use is one of them is trust. So trust is a force, but trust also can be used in terms of power. Okay, in watt. But here is a force. Okay, so trust. Um, I'm not going to explain to you how mathematically, theoretically, how the scientists derive this trust force. But there is the step by step, the mathematics step. But I think that is not very important for you to know that. At least you understand how they derive it. Where does it come from? Okay, the mathematic one by one step. I think you can look at in the any reference book they have. Okay, but here, okay, for example, we have the engine. So our engine here, aduh, alamak, sorry. So our engine here, this one in white. This is our example of our turbofan engine or engine. Okay, our propulsion device, the engine. Okay, so we imagine the engine, the propulsion device here is the closed system. So that's why we need to learn about the closed system first. So we our control volume, the closed system. So we imagine that this engine, the propulsion device, is our control volume. So we have to analyze the system, the control volume. Okay, we look at it and see what are the mass, the heat transfer in and out, the energy transfer in and out of our control volume, the system, which is the engine, the propulsion device. So here, by looking at the control volume, the engine, we know that we have force, the pressure force, PA, pressure force, okay, inlet and outlet, or from left hand side and right hand side, kan? So we have pressure force as a thing on the control volume, the propulsion device, okay, the pressure force here, okay, pressure force uh, here and here. Okay. From this is the initial point inlet, which is known as O, and exhaust E, exit E. Okay, so we have those pressure force. Okay, right and left, inlet, outlet. Okay, so because pressure is force over area, so pressure force is PA. Okay, and the mass, the mass, inlet, outlet. Okay, so this one, okay, the mass or the momentum here, because we change it into force, so is m dot v, the momentum. So there is mass, inlet and outlet, okay, at the location O and location E. Okay, so this is the sum of the force exerting on the control volume propulsion device. Okay, so we have this equation here. Okay, so this equation is what we call thrust force. Okay, so this is the equation of the thrust force. Okay, from resulting from the control volume here. Okay, so if we assume, or if we have the exhaust pressure PE here equals to PO, then the thrust force equation is simplified to only this one. only the momentum equation. Okay. And we have also specific thrust. Specific thrust is the thrust over mass flow rate of the air. Okay, this is another parameter, another properties which is written here, specific thrust. But specific thrust is commonly used more for rocket. Okay, to evaluate the performance of the rocket, commonly we use specific thrust. But for aircraft engine, normally we calculate the thrust force or thrust power. Okay, so these are the factors affecting the thrust. You can look at here, jet nozzle. So it depends on the jet nozzle, it depends on the air speed, it depends on the mass airflow. So actually all of this related to pressure and temperature. Pressure, temperature, pressure, ambient. PAMB is ambient. Okay, ambient. Okay, so look at the density. So these are the 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 factors, the parameters that affect the thrust. So whether we are at the higher altitude or lower altitude, right? Higher altitude, of course, less density decrease, normally temperature rise. We imagine that we have water, gas, right? So gas normally less density, but it has higher temperature than water normally. Okay, so water has more dense. So it's like that. Just imagine like that. Okay, so you understand. So these are the factors affecting thrust. So means that the thrust can be changed depends on these factors. And then engine design objective. Okay, so these are um, what we call the engine design objective. So in order to design an engine, so we need to take into consideration these parameters, especially this one. Okay, the specific thrust here. Okay, this is where the aircraft propulsion course is important. Okay, because in order to design the engine, we need to consider the lift, the drag, this is aerodynamics. What you learn in aerodynamics. This one is where you learn in aircraft propulsion. Okay, we're going to finish. So this is another other parameters that are usually used to evaluate the performance of aircraft engine are propulsive efficiency, noted as ETAP here. Is written, actually there is several different equation method to calculate propulsive efficiency, but these are some of the example. Okay, so propulsive efficiency used to calculate to evaluate the efficiency of the engine. So it's written as thrust power over the thrust power plus the power wasted, the total power. Okay, so it's written like this. Okay, U is the speed and T is thrust. This one is speed, air speed, air speed. T is thrust. Okay, so this is at the exit. This is mass flow rate. Okay. If ideal case, if nozzle is unchoked and F is negligible, then we can use this simplify propulsive efficiency. Okay. But if F is the fuel to air ratio, which is written as MF. MF over MA. Okay, fuel to air ratio. So if F is negligible, means that this mass flow of the fuel is very, very small compared to MA. So F is negligible. And if nozzle is unchoked. Okay, nozzle is unchoked means that PE, the exit pressure, is equal to ambient pressure. So we can use this simplified or ideal case propulsion efficiency. Okay, this is the simplified version. The longer version is this one. Okay, last one, propulsion efficiency. Okay, so this is the explanation on the propulsion efficiency. So propulsion efficiency is the energy contained in a vehicle's propellant. The energy contained inside the propellant, okay, is being converted into useful energy. So how much the energy inside of the propellant is being really converted into useful energy. Okay, because we are more interested in useful energy, the thrust power produced. Okay. So propulsion efficiency also is the proportion of the mechanical energy actually used. Okay, again, useful. Okay. So, and then we also have this parameter, this extra parameter, thermal efficiency. Thermal efficiency is to characterize, to evaluate the efficiency of the combustion process. Okay, because it is concerned the thermal energy part, which occurs in the combustion chamber. Okay, so we have all those equation for ramjet, turbofan, turboprop. Okay, but the common that we use is for turbojet here, turbofan here, and also turbojet. Okay, the definition is here. Overall efficiency, specific thrust just now, overall efficiency is thermal efficiency multiplied with propulsive efficiency. We also have specific thrust just now, like I mentioned. This is thrust, and the specific fuel consumption. Yeah, this is again another important parameter. Thrust specific fuel consumption, or sometimes it is written simply specific fuel consumption. So thrust specific fuel consumption is to measure the ratio of is to measure how in order to produce 1 Newton thrust force, how much fuel mass flow rate we need. Okay. So SFC is to measure how much mass flow rate, the fuel mass flow rate, fuel mass flow rate that we need to produce 1 Newton thrust force. Okay. So means that we want to achieve a low value of the SFC as much as possible. Low value as much as possible, because if you have low value with SFC, means that we use less fuel. That is our objective. One of our objective, way to identify whether the aircraft engine is performing good or not, good in performance or not. Means use less fuel, less TSFC. Okay, so these are the summary of this chapter. Investigate the operating principle, analyze open cycle single shaft, analyze multi-spool, discuss gas turbine design procedure. Okay, I think that's all. Okay, that's all from me. But actually, I have assignment for you to do. Okay, that need to be done in 3 weeks. Means need to be submitted in week 5. Okay, week 5, which is week 5 is in November, around 18 November. I will upload the instruction. Is easy. Okay, you need to do some literature review on the heat recovery on the gas turbine cycle. Okay, you need to do in group literature review of the gas turbine cycle, and we prepared reports. Okay, I will write down the instruction in the assignment slides. I already share with assignment slides. Just to mention that you have assignment to do in and to submit in 3 weeks. Okay. I will share the instruction in other slides. Okay. Okay, that's all from me. Thank you very much. Bye bye.